Hello students. Hello and welcome to this video. In this video we will solve question number 91 to 100 of binomial theorems. The link to download the PDF will be in description, as well as at the end I will show you how you can download the book from the website among other books and my question answer website which I have prepared for you guys. So without further ado, let's get started. Question 91 says that we have to prove that C0 minus 2 times C1 plus 3 times C2 and so on up to minus 1 to the power n plus 1 Cn is equal to 0. So this is the given series, and rth term would be minus 1 to the power r minus 1 r times ncr minus 1. This we can write as minus 1 to the power r minus 1 ncr minus 1 plus minus 1 to the power r minus 1 ncr minus 1. That is minus 1 to the power r minus 1 n times n minus 1 c r minus 2 plus minus 1 to the power r minus 1 and c r minus 1. So this entire series becomes the sum of these two numbers, where r varies from 1 to r plus 1. Once we have that, we can, the first term, this series becomes minus n times n minus 1 c0 minus n minus 1 c1 and up to minus 1 to the power n minus 1 c n minus 1 c n minus 1. And the second one, this one becomes nc0 minus nc1 plus nc2 up to minus 1 to the power n minus 1 ncn. And both are expansions of minus 1 minus 1 to the power n or n minus 1, which is 0. The calculus method is we let 1 plus x to the power n is equal to c0 plus c1 plus c2x up to cn xn. We multiply with x and differentiate with respect to x to get 1 times 1 plus x to the power n plus h times n times 1 plus x to the power n minus 1 is equal to c0 plus c1 2x plus c2 times 3x square up to n plus 1 cn x to the power n. We put x is equal to minus 1 and we get the desired series. Question 92 asks us to prove that C0 minus 3C1 plus 5C2 up to minus 1 to the power n times 2n plus 1 Cn is equal to 0. So given series is this one, and rth term we write as minus 1 to the power r minus 1 2r minus 1 c r minus 1, which is equal to minus 1 to the power r minus 1 2 times r minus 1 plus 1 c r minus 1, which upon further simplification we can write as 2 times minus 1 to the power r minus 1 and n minus 1 c r minus 2 plus minus 1 to the power r minus 1 and c r minus 1. So the given series, that is this one, becomes the sum of minus 1 to the power r minus 1 n minus 1 c r minus 2, where r varies from 1 to n plus 1 plus n c r minus 1. Now we add these two, we get minus 2n times n minus 1 c0 minus n minus 1 c1 up to minus 1 to the power n minus 1 c n minus 1 plus this particular series becomes c0 minus c1 plus c2 up to minus 1 to the power n cn, which is equal to 2 to the power n 1 minus 1 to the power, this should be n minus 1. 1 is missing here, plus 1 minus 1 to the power n, which is equal to 0. The calculus method is that we take the expansion of 1 plus x squared to the power n, which is c0 plus c1 x squared plus c2 x4 up to cn x to the power n. Multiply both sides with x and differentiate. Left hand side will become c0 plus 3c1 x squared plus 5c2 x to the power 4 up to 2n plus 1 cn x to the power 2n, which is equal to, let me think a bit. Yeah, that is true. But I do not see how this becomes minus 1. This will remain plus 1, right? Yep, no, this is not correct. So c1x square is cubed. No, this is not correct. This will remain positive. Okay, this will remain positive. So what should be done is you should put x is equal to I here rather. the complex number I. If you put I, it becomes 1 minus 1 to the power n. This also becomes 1 minus 1 to the power n. And this becomes minus 3c1, and this remains 5c2 plus 5c2, then minus 7c3. So you put x is equal to I. This substitution is wrong here. And thus we have the required series. Question 93 says that we have to prove that a minus 1 c1 plus a minus 2 c2 minus a minus 3 c3 up to minus 1 to the power n a minus m cn is equal to 0. So given series is this one, okay, and we take the rx term is minus 1 to the power r minus 1, a plus 1 minus r times nc r minus 1, which is equal to minus 1 to the power r minus 1, a minus r minus 1 c r minus 1, which is equal to a to the power minus 1 to the power r minus 1 c r minus 1 minus 1 to the power r minus 1 n times n minus 1 c r minus 2. So this entire series becomes sigma r is equal to 1 to n plus 1 minus 1 to the power r minus 1. Of course, a is outside, c r minus 1 plus minus n times sigma r is equal to 1 to n plus 1 n plus 1 c r minus 2. Now we substitute the expansion. We get a times c0 minus c1 plus c2 up to minus 1 to the power n cn minus n times n minus 1 c0 minus n minus 1 c1 plus n minus 1 c2 up to minus 1 to the power n minus 1 cn minus 1, which is equal to a times 1 minus 1 to the power n minus n times 1 minus 1 to the power x n minus 1 equal to 0. For the calculus method, we have this left hand side, which is equal to a times c0 minus c1 plus c2 up to minus 1 to the power n cn plus c1 minus 2 c2 plus 3 c3 up to plus minus 1 to the power minus n times cn. We have shown these two series in bracket earlier equal to 0, and that's how we get this equal to 0. Question 94 says that we have to prove that 1 square times c1 plus 2 square times c2 plus 3 square c3 plus n square cn is equal to n times n plus 1 2 to the power n minus 2. So here the sum has to be shown to be n times n plus 1 to the power 2n minus 2. Now we take tr, which is r squared times cr, which is equal to r times n times c n minus 1 cr minus 1, which is equal to n times r minus 1 plus r minus 1 plus 1 n minus 1 cr minus 1, which is equal to n times n minus 1 n minus 2 cr minus 2 plus n times n minus 2 cr minus 2. Now we clearly see that this sum is equal to n times n minus 1 2 to the power n minus 2 plus n times 2 to the power n minus 1, which is equal to n times n plus 1 times 2 to the power n minus 2. In the calculus method, we first differentiate by x. We get c1 plus 2 c1x plus 3 c2x square up to n cn x to the power n. Now we multiply both sides by x and differentiate again with respect to x. We get n times 1 plus x to the power n minus 1 plus n minus 1 x 1 plus x to the power n minus 2 is equal to 1 square times c1 plus 2 square times c1x plus 3 square times c2x square and so on up to n square cn x minus 1. We substitute x is equal to 1, we get the sum as n times n plus 1 times 2 to the power n minus 2. Question 95 says that if n greater than 3 and n is in the set of natural numbers, we have to prove that c0 times abc minus c1 times a minus 1 b minus 1 c minus 1 c2 times a minus 2 times b minus 2 times c minus 2 minus so on up to minus 1 to the power n cn a minus n b times b minus n times c minus n is equal to 0. So this is question number 95. Okay. There seems to be something wrong here. This is not the correct solution. Sigma PR plus 1. No, this is not correct solution. This is 96 actually. So 96 is the 95. Okay, the numbers, the solutions got exchanged. So we have this as the series. So TR plus 1 is minus 1 to the power R, ABC plus A plus B plus C R square minus AB plus BC plus CA minus R minus R cube and CR. Now we look at minus 1 to the power R NCR is equal to C0 minus C1 plus C2 up to minus 1 to the power N Cn is equal to 0. So this covers the multiple of ABC. Now we take this one, that is RCR. S is equal to sigma R is equal to 0 to, this should be R is equal to 1 actually. R is equal to 1. So NC n minus 1 C R minus 1, you get minus n minus 1 C0 minus n minus 1 C1 and so on. There is a typing mistake here. This should be n minus 1 C2. We get the sum as minus n times 1 minus 1 to the power n minus 1 is equal to 0. Again, this should be from I is equal to 1, this should be I is equal to 1 and so on. So essentially, we represent R square NCR as R times n minus 1 CR minus 1, which we further represent as R minus 1 n minus 1 CR minus 1. And this further reduced to n times n minus 1 CR minus 1, which is again 0. And similarly, R cube 1 is also taken as 0. So that ABC, NCR, R square, NCR, R, NCR, and R cube, NCR are all equal to 0. And that is how left side sum is equal to 0. Now we look at question 96. C0 minus 2 square C1 plus 3 square C2 up to minus 1 to the power n plus 1 whole square Cn is equal to 0 and is greater than 2. So here TR plus 1 is minus 1 to the power R square C R. This should be TR actually. This should be TR, not TR plus 1. Now this is equal to minus 1 to the power R square plus 2R plus 1 CR. So let me think a bit. So if this is actually TR plus 1, this should be R plus 1 whole square. Okay. This is R plus 1 whole square and this CR is good. Then this expansion is good. Now we take this. Now we consider minus 1 to the power R times 1 times CR. So this is equal to C0 minus C1 plus C2 up to minus 1 to the power n Cn, which is equal to 0. Now we consider the middle term minus 1 to the power R RCR is equal to minus 1 to the power R n times n minus 1 C n minus 1 R minus 1. So this should vary from R is equal to 1 to n. So we see that this sum is this, which is equal to 0. And then we take the R square one, and like the question 96, we have proven this to be 0 as well. So 95 and 96 are quite similar. The solutions got exchanged. I'll fix this and then we can see. Also, in some of the sums, the indexes are not good. So I'll fix the indexes. Here R should be 0, here R should be 1, and 1 to n, yes. And here it should be from 2 to n. This should be 2 to n. Now we move on to question 97. Prove that sigma R is equal to 0 to the power n, not to the power n, sigma R is equal to 0 to n R square TR 2 to the power R 2 to the power n minus R is equal to np cube plus n square p square if p plus q is equal to 1. So we are given this term which we can write as R dot n minus 1 C R minus 1, which further it gets reduced to n times R minus 1 plus 1 n minus 1 C R minus 1. The powers of PQ are same, so I'm not taking that. So we take this n into n minus 1 n minus 2 C R minus 2 plus n minus 1 C R minus 1, which becomes n times n minus 1 p square C n minus 2 R minus 2 p to the power R minus 2 q to the power n minus 2 minus r minus 2 plus np n minus 1 n minus 1 c r minus 1 p to the power r minus 1 q to the power n minus 1 r minus r minus 1. So this essentially becomes sigma tr plus 1 becomes n times n minus 1 p square p plus q to the power n minus 2 plus np p plus q to the power n minus 1, which is equal to n into n minus 1 times p square plus np, which is equal to n square p square plus np. There should be q here. Okay. So this, there may be some timing mistake here. So please adjust your answer accordingly. So p plus q is 1. P plus q1 means this is equal to n into n minus 1 p square, and this becomes np. Yeah, looks good to me. Question 98 says that we have to prove that 2 times C0 plus 2 square upon 2 C1 plus 2 cube upon 3 C2 and so on up to 2 to the power 11 upon 11 times C11 is equal to 3 to the power 11 minus 1 upon 11. So this we have solved earlier, I believe. Let me see this one, okay? Like question 80 here, instead of n we have 10 to the power 11 upon 11. Yeah, like 80. So like 80 you solve 98 and it will be there. Now we look at question 99. It says that we have to prove that 2 square upon 1 dot 2 C0 plus 2 cube upon 2 dot 3 C2 plus 2 to the power 4 3 dot 4 C square is equal to, and so on up to 2 to the power n plus 2 upon n plus 1 times n plus 2 Cn is equal to 3 to the power n plus 2 minus 2n minus 5 upon n plus 1 in times n plus 2. So this is what we have to prove. So we take that is term is 2 to the power r plus 1 upon r times r plus 1 times ncr minus 1. This we can write as 2 to the power r plus 1 upon r plus 1, and this becomes n plus 1 cr upon n plus 1. And this we further write as, there is something wrong here. Then we further write this as 2 to the power r plus 1 upon n plus 1 times n plus 2 cr plus 1 upon n plus 2. So we take the sum and this becomes equal to this one. And then we r is equal to 1 to n plus 1 we vary, and then this becomes right hand side. We substitute finally. No, we don't substitute. This becomes 2 square n plus 2 C2 plus 2 cube n plus 1 C3 up to n plus 2 n plus 2 C n plus 2 C n plus 2. And so, hang on, from where this came. Okay, this comes from this only, okay? So this entire thing is equal to sign is missing here. 1 plus 2 to the power n plus 2 and minus first two terms, that is n plus 2 C0 is not here and n plus 2 C1 is not here, so we added and subtracted that, which is equal to 3 to the power n plus 2 minus 2n minus 5 upon n plus 1 times n plus 2. So this is 3 to the power n plus 2 and these two becomes minus 2n minus 5. So this is basically 1 and this becomes n plus 2. Okay, so that's how we have that. Now we look at the calculus method. 1 plus x to the power n is equal to C0 plus C1 plus C2 x square up to Cn xn. We integrate within limits 0 to x, you get this as the series, and right hand side is there. And we integrate again within limits 0 to 2, so we get 2 square upon 1 times 2 C0, that is the left hand side is equal to right hand side. Now we come to question 100. Question 100 says that C1 minus C2 upon 2 plus C3 upon 3 up to minus 1 to the power n Cn upon xn is equal to 1 plus 1 plus 2 plus 1 plus 3 up to 1 plus n. So we let Sn is equal to left hand side is equal to n minus 1 upon 2 times n minus n into n minus 1 upon 2 plus 1 upon 3 times n into n minus 1 into n minus 2 upon factorial 3 and so on. So our right hand side becomes n minus 1 plus 1 minus half into n minus 2 times n minus 2 plus 2 upon 2 factorial plus 1 upon 3 into n minus 1 into n minus 2 into n minus 3 plus 3 upon 3 factorial and so on. So we write this as n minus 1 in minus half times n minus 2, n minus 1 times n minus 2 upon factorial 2 plus 1 upon 3 times n minus 1 times n minus 2 times n minus 3 upon factorial 3 and so on. Plus we bring this one here and it is 1 minus n minus 1 upon factorial 2. We bring n minus the n minus 1 term from here to here. The other half of that 2 factorial. So half is here and half is here. So this term is split into 2. All the terms are split into 2. So eventually the sum becomes Sn minus 1 plus 1 upon n, C1 minus C2 plus C3 minus and so on. That is Sn minus 1 plus 1 upon n. So Sn minus 1 is equal to 1 upon n. So Sn1 minus Sn minus 2 is equal to 1 upon n minus 2 and so on. And thus we have the required sum. Now the calculus method is 1 minus C1x plus C2x squared plus C3x cubed up to minus 1 to the power n Cn xn is equal to 1 minus x to the power n. So we have this as this sum as 1 minus x to the power n upon x. So integrate between limits 0 to 1 and you get the desired series. Okay. With this we come to the end of question 91 to 100. And now I'll show you my website astrolocker.org and you can download the algebra, trigonometry and coordinate geometry PDFs from here. Note that when you download the PDF they won't have date. So you need to add date to those. And you should come and visit between 15 or 30 days and see if the book has been updated. If it is updated, you can download the next version and update the date on your PDF. I cannot put the date in the link because that will make the existing link invalid. Also, if you want to ask questions to me, you can come and click the H link, that is Punjika. So this is a web application which I have developed for you, where you can ask mathematical questions because YouTube comments are not suitable for mathematics. So you have got tags here: algebra, calculus, coordinate geometry, probability, and trigonometry. The web application is fairly simple to use. You make a login, you ask questions, you answer questions. So that's the simple thing you have to do if you want to ask questions. So with this, I will end this video here. I see that there are lots of typing mistakes in this one, so I'll fix those and update the PDF. So probably in a day or two, I'll update particularly indexes are wrong at many places. So I'll update the PDF and I'll end this video here. I'll see you in the next one with 10 more problems on binomial theorems. So thanks a lot for watching and keep learning, stay curious, and most importantly, enjoy.